Okay, folks. For today's goal, you're going to hopefully be able to identify different forms of energy as potential or kinetic energy. And then I also want you to understand that energy cannot be created or destroyed, but only converted into different forms. For the agenda today, you're going to take notes on energy, and then you're going to complete the practice problems. There's a couple in the middle, and there's one at the end of the assignment. Okay, so what do you think of when you hear the word energy? Go ahead and pause the video for a second. Tell me what you think of when you hear the word energy. Energy is defined as the ability to do work. There are two main types of energy. We call them kinetic and potential energy. Things with kinetic energy are moving, so kinetic means moving. Like if someone's telekinetic, they can move things with their mind. If someone's a kinesiologist, they help people with, if they're having joint trouble so that they can move their, arms and legs. Okay, things with potential energy have the potential to move or the potential to do something, at least. Potential energy is sometimes referred to as stored energy. And then the last thing that I want you to know is that energy can never be created or destroyed. It can only be transferred or converted from one form to another. And we'll see that in today's lesson. Okay, so some examples of kinetic energy. First one is called translational kinetic energy. It's a big word. It's a big term. It's not really that as confusing as it sounds. It just means things moving forward and back, left and right, up and down. Right? So when you think of something moving, you're probably thinking of something moving with translational kinetic energy. Next up is rotational kinetic energy. Right? If we think about a propeller spinning around, that has rotational kinetic energy because it's spinning, or like a ball rolling, that would have rotational kinetic energy, or a wheel. Right? Lots of examples there. Vibrational kinetic energy. If you've got an electric toothbrush, you know that sort of like vibrates up and down to brush your teeth. Anything that vibrates has vibrational kinetic energy. Next up is thermal energy. So that's like heat. And so if you think about little gas molecules moving around in the air, if you heat them up, what happens is those molecules actually move faster. So the faster things are moving, molecules, atoms, the faster those subatomic particles are moving and vibrating and rotating, the more thermal energy they have. Electrical energy, so that's like electrons moving through a circuit, right? So that's another form of kinetic energy, electrons moving through a circuit. And then light energy, right? Remember that light is just a little particle moving in a wave pattern through space. We call that particle a photon. Okay, so then examples of potential energy. Gravitational energy, right? Think about like this pineapple sitting on a table. It has the potential to fall down, right? If I push it. Right now it's not moving, but if I pushed it, it would fall and then it would be moving. Elastic energy, right? So if you remember from the Newton's third law lab, we pulled back those elastic rubber bands, right? And then when we cut the string, they move forward. But while they're pulled back, they have the potential to snap back forward. And so we call that potential energy, or elastic potential energy. Chemical energy. If you think about the food that you eat, that food has energy stored in the chemical bonds. Right? And your body is able to break down those chemical bonds for energy so that you can do stuff like run around and think and do science. Right? So chemicals have energy stored in them. Same thing like if you think about like your car burning gasoline, that gasoline has energy in it, and that energy allows the car to move forward. Right? A battery has chemical energy in it, and then when you hook it up to a circuit, it's converted into electrical energy. Nuclear energy. So if you think about the nucleus of an atom, that has energy stored in it as well. And when it breaks apart, you can collect some of that energy, and we call that fission. So that's how we get energy out of like a nuclear reactor. Okay, and so then we're going to label each object here as having kinetic or potential energy and then explain why it's kinetic or potential energy. If we think about a car that's being driven, that's kinetic energy. Why? Because the car is moving. So really, for kinetic energy, all the ones that are kinetic energy, they should have something moving in them, right? That should, your explanation should be that the object is moving. A stretched rubber band has potential energy. Why? The band has the potential to snap back, right? So think about a rubber band like this. If we pull it, right, it's not moving at the moment, but we know that if I let it go, right, it's going to snap back. So it has the potential to move. It has the potential to do something. So every single one of these, as you go through them, they're either going to be kinetic or potential. If they're kinetic, it's because they're moving. If it's potential, it's because they have the potential to do something, and you have to say what they might do. So think about it. If you're confused about the explanations, at least try to identify each one as kinetic as potential, and we'll go over the explanations as a class. Okay, so let's go through an example of potential energy being converted into kinetic energy. Remember, energy is never created or destroyed, it just converts into different forms. So if we think about it, this person standing on top of a box holding a ball, that ball is all potential energy right now, right? And that's because the ball's not moving, but we know if she lets it go, it would have the potential to fall down. So go ahead and fill in your circle blue, and then make a little key over here that blue means potential. Okay. Now on the next slide, she's dropped it, and it started to fall down a little bit. We'll say maybe it's a quarter of the way down. So now at this point, the ball has some kinetic energy because now it's moving. It started to fall down. But it also still has some potential energy, right? Because it's still above the ground. It still has the potential to go even faster as it continues to fall. And so the way you want to color your graph at this point is make 1/4 of it kinetic and make the rest of it blue for potential. That makes sense? So 1/4 red, the rest is going to be blue. Right? Now it's fallen halfway down, so it's going to be half potential, half kinetic. Right? The further it falls down, the faster it's going to be going, so we're going to be seeing more and more kinetic energy. Now it's fallen the 3/4 of the way down, so it's going to be 3/4 kinetic and 1/4 potential. And now it's just about hit the ground. It's like an instant away from hitting the ground, so now it's all kinetic energy. There's no more potential energy because it's pretty much on the ground. It's moving as fast as it's going to go. So hopefully that makes sense. Let's go through one more example. Hopefully this will clear it up if you're confused at all. Oh, whoops, sorry, we've got to answer a few questions first. So when did the ball have the most potential energy? Well, that was at the top, right? That was when we filled in our graph all blue. When did the ball have the most kinetic energy? Well, that was at the bottom, right? Position E. When did the ball have both potential and kinetic energy? Well, that would be at the middle 3 points, right? When it was falling, but not all the way to the ground. So that would be at positions B, C, and D. Next question, when did the ball have the least potential energy? Well, it had the most potential energy at point A, right, when it was at the top. So then it must have the least potential energy at point E, right, when it's at the bottom. When did the ball have the least kinetic energy? Well, again, that's going to be at the top when it wasn't moving, right? When she was holding on to it. When something's not moving, it's not going to have any kinetic energy. So we'll say at position A. Okay, let's keep going. Example 2 of the potential energy being converted into kinetic energy. We've got this example of a spring sort of bouncing up and down with a mass on the end. So let's kind of take a look at that and see what that actually looks like in real life. So here, let me move back a little bit. So here I've got a spring with a mass on the bottom. And so you can probably guess that if I pull it down, what's going to happen is it's going to bounce up and down a little bit, right? Move up and down. And so the idea here is we're going to look at three positions. The first position is, where would the spring be if it was just hanging? Right? So that's like that. The last position is, where would it be if I pulled it down a little bit? And then if I let it go, whoops, if I let it go, it's going to be bouncing up and down. So when it's at the top position, it's what we say, well, when it's at the middle position, it's we would call that at equilibrium, right? So in the middle. And so when the spring is compressed, like here, or when it's stretched, like here, what's going to happen is the spring's going to have some elastic energy, right? Just like the rubber band, right? And so because it has elastic energy, it will have the potential to make the mass move. So let's look at that in a little bit more detail. So we're going to start with it at the very top position here, where the spring is compressed a little bit. In this position, there's going to be two types of potential energy. So there's going to be gravitational. That's because the mass is up in the air a little bit. But it's also going to have some elastic energy because the spring is compressed. Right? The spring is like squished together. All right, so in the next one that we look at, we're going to say that the spring is at equilibrium. So it's lost a little bit of gravitational energy, right, because it's moved down a little bit from the last slide. So we've lost some gravitational energy, right? It was 50% gravitational energy. Now we're only at about 25. But it's gained kinetic energy. When the block is in the middle, that's actually when it's moving fastest. When it's vibrating up and down like that, it's actually moving fastest when it's in the middle there. Okay, and then last up is going to be when the block is at the very bottom here. Well, now it's not going to have any gravitational energy, right, because it's at the lowest point. It's as far down as it can go, so no gravitational energy. However, it's not going to have any kinetic energy either, because the block isn't moving when it's at its highest or its lowest point. It's standing still at those two instances. So really, the string is stretched at this point. So all of the energy is going to be converted into elastic energy, and it's just energy from the string, or from the spring being stretched out. Okay, so then let's answer some questions. When did the block have the most gravitational energy? That would be at A, right, when it was at its highest point. When did the block have the most elastic energy? That was at point C, right, when the spring was the most stretched. And then when did the block have the most kinetic energy? That was at point B, right? It's moving fastest when it was in the middle there, because the most energy had been converted into kinetic energy at that point. So when did the block have the least gravitational energy? Well, that would be at the bottom, right? There's no potential for it to fall any further at that point, so that would be at point C. When did the block have the least elastic energy? That would be at point B, right? Because the spring isn't stretched or compressed at all. The spring is relaxed. It's at its equilibrium point. And when did the block have the least kinetic energy? Well, that would be at 2 points, at point A and at point C. It didn't have any kinetic energy at those points. It wasn't moving. So when the block's bouncing up and down, it's actually not moving at point A or point C. Okay, and so then in the next one, we're looking at a pendulum. You go ahead and try and figure out the different energy positions for